I hope all is well for you. Today we will see how does light have momentum without having any mass. Isn't that a contradiction? Welcome to the Question Answer channel, the channel where you will find the answer to everything. Today's answers will be presented by Kip Ingram, Kevin R. Martin, Victor T. Toth and Andy Diamond. We'll start with the first answer by Kip Ingram.
You feel the way you do because you were taught in high school that momentum is mass times velocity. But that turns out to be an incomplete picture of momentum. When you study higher physics, relativity in particular, you learn that mass is not required for there to be momentum, and in cases where the mass is zero you use a different formula to calculate it. First of all, the high school definition isn't even completely correct for objects with mass. It doesn't take into account relativistic effects. The correct equation is P equals m asterisk v, sqrt, 1v squared, c squared. For small velocity, which is what you talk about in high school, this converges to P equals m asterisk v, the formula you're familiar with. Objects without mass must travel at the speed of light. But look what happens to this expression if you substitute v equals c. The denominator goes to 0. The numerator does too, for m equals 0, so you wind up with 0 over 0, which is undefined and could be anything. So this formula places no restrictions on the momentum of a massless object. It's just unusable and we have to turn to other ideas. For massless objects, the momentum is Planck's constant divided by the object's de Broglie wavelength. So, your intuition steers you wrong here because you were never taught the full set of ideas. Stay safe and well, Kip.
What do you think? We will continue with Kevin R. Martin's answer.
Good question. First off, what does the word momentum mean? Newton defined the word momentum to mean the mass of an object times the object's velocity, not speed. In his day, that definition was very useful because it led to accurate predictions of the motion of known objects, as well as fruitful new ideas such as the conservation of it. You are most likely thinking along these lines as to what momentum is. Well, we have advanced since the 17th century and have discovered new things. For example, we know Newton's definition isn't quite right. We have since corrected his mistakes. Einstein figured out that the better definition is momentum equals gamma times rest mass times velocity. Let's carefully go through each of the three terms. First, gamma is, where versus is the speed of the object and the symbol c means the speed of light in vacuum, which is very, very fast. Note we aren't talking about light, but just what the momentum is for any old object around you. A baseball, a car, the moon. Just think of c as a constant, a really large constant that just has to be there cause Newton wasn't quite right about what momentum is. For everyday objects you see around you, gamma is practically 1. But it's still in the equation. Newton didn't know it was there because he had no experience with objects that move really fast. Second term, rest mass. This means the measured mass of the object when the object is stationary relative to you. Newton never made this distinction because he thought mass was mass. Finally, velocity. Same as what Newton thought. So, there were two improvements, the inclusion of gamma, even though for common everyday movement around you, it is 1, and the distinction that whatever went in for the mass, it had to be the measured value when the object was stationary. Notice something unusual about the improved version of momentum. If the object is moving with speed c, very, very fast, the momentum becomes infinite. Okay, back up a little, say the object is moving at 99.9% the speed of light. Gamma is a large number, but not infinite, so the new improved version of momentum says such a fast-moving object has more momentum than Newton thought. Back to something moving at the speed of light. Well, light does that. So does light have infinite momentum? That seems to be the prediction here. What about the rest mass of light? Well, that would be the rest mass of a photon. Guess what the rest mass of a photon is? You got it, it's 0. So the new improved version of momentum gives a 0 over 0 for light, which the mathematicians call indeterminate. In math, it's possible 0 over 0 is 0, a finite number, or infinite, depending on how the two zeros are approached. Now what? Well, more work. Einstein figured out the relationship between the energy carried by a free object and the momentum that the object carries is m means rest mass. The photon has 0 rest mass, so we finally get something for light. E equals pc. So light must have a momentum of p equals e, c. This is amazing simple, much simpler than the momentum of a baseball with all the gamma stuff and rest mass stuff. Whatever the energy of the light is, just divide it by c, and that is how much momentum it has. We also know that a particle of light has an energy of hf, or if you prefer wavelength to frequency, hc, wavelength. So the momentum of a particle of light is p equals h, wavelength. So, no, it is not contradictory to say light has momentum and say at the same time the mass of light is 0. In reality, if something has 0 rest mass, that something must have momentum and it must be the amount of the energy divided by c. Another way of saying it is that Newton's definition of the word momentum wasn't quite right and had to be corrected as we gained more knowledge over the 300+ years since Newton. Yes, Newton was not absolutely right, and we have improved on him. And, in the end, doing experiments and observations to see if all this theoretical stuff is right is what matters. Well, it's been tried, and confirms that P equals E, circa for light. In essence, how Newton defined momentum works pretty good for everyday objects moving relatively slowly. The faster and faster an everyday object moves, say a baseball, the more and more Newton is off. And for light, Newton was way off.
The following answer is from Victor T. Toth.
Oh, so you paid attention in high school. Momentum is mass times velocity. Good, and it is indeed true. In simple physical scenarios that do not involve relativistic velocities. But contrary to what your science teacher may have told you, this is not the definition of momentum. In fact, the formal definition gets rather complicated and involves Lagrangian and Hamiltonian physics, so let me just present one of the results, the relativistic momentum of a point particle. P equals mv, 1 minus v, 2, slash, c, 2, minus, 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 square root, p equals mv, 1 minus v2, c2. In the non-relativistic limit, v, c, is very small, the denominator becomes approximately 1, and we get back p equals mv, but this is not true for particles moving at or near the speed of light. So far so good, but even this expression for the relativistic momentum won't do the trick for the photon, since m equals O, and v equals c, we just get p equals 0 over 0, which is indeterminate. That is a step in the right direction, at least it's not 0, but not enough. So then, what else can we do? Well, there is another relationship involving momentum, the so-called dispersion relation, which says that E2 minus PC, closing parenthesis, 2, equals MC2, closing parenthesis, 2, E2 minus PC, 2 equals MC2, 2. You might have seen a simpler form of this relationship expressed in the particle's rest frame where P equals O, colon, E2 equals MC2, closing parenthesis, 2, E2 equals MC2, 2. Or simply, A equals MC2, A equals MC2. Familiar, no? But this form does not apply to the photon, because photons have no rest frame. Instead, for photons, m equals O, hence we are left with E2 equals PC, closing parenthesis, 2, E2 equals PC, 2. Or, P equals A, C. And that is the momentum of the photon, or indeed, any massless particle, which has no mass, but has energy and moves at the vacuum speed of light.
The following answer is from Andy Diamond.
They just do. It's a different formula, P equals A, C, where A equals the usual HF. Check out Einstein's special relativity, it's basically from the same formula that gives us A equals mc squared. Just because P equals mv for massive particles, it does not mean that is the end of the story. Neither formulae actually tell you why particles have momentum, only how much they have. It tells you that momentum in itself is not a property of mass alone.
This is the end of the video. I hope you have more answers. If you found the answer you were looking for, please leave a like and subscribe, it would help us a lot. Friends, it's now the end of this video. Remember to leave a comment to tell us if these answers are more for you. See you soon.